I can't say that we have completely captured everything that could be said about core collapse supernova, but it's all we're going to have time for. Just as with planetary nebulae, you can talk about the light show, the planetary nebula, but then you want to know what happens to the star's core. We left our star's core collapsing. What happens in the somewhat more energetic, high-mass version of core collapse? We know that electron degeneracy is not going to rescue our collapsing iron core. Electrons are essentially gone. Luckily, neutrons, like electrons, are fermions. They too are subject to the Pauli exclusion principle. They too exert a degeneracy pressure that is proportional to the 5/3 power of their density. A little more careful analysis shows that because in the confines of the collapsing core, these neutrons are in fact relativistic, then like electrons, there are corrections to this 5/3 rule. It's more like 4/3. But they're subject to the same kind of degeneracy pressure, and it turns out that neutron degeneracy pressure, you can think of that partially as the repulsive core. It's essentially equivalent as the repulsive core of the strong force. Remember, we saw that attraction down to an optimal distance of about 1 Fermi between nucleons, and then a repulsive force when you tried to force them too close. This is essentially the same, because that was a quantum treatment, as the Pauli exclusion principle. At a density of 6 to 7 times 10 to the 17 kilos per meter cubed, neutrons become degenerate and the core stops. If you imagine that the core had sort of a stellar mass, let's give it the mass of a heavy white dwarf, then at this density, your white dwarf with a radius essentially that of the Earth will have collapsed to something with the radius of a city. So now we're talking about essentially a great big nucleus, very, very rich in neutrons, made containing a solar mass in a ball of radius 10 kilometers. Clearly, the gravitational effects are humongous. The surface gravity, if you compute it classically and ignore incorrectly relativistic effects, will be on the order of 10 to the 11 or 10 to the 12 G. You certainly do not want to go stand on this object. The physics, as I said, is relativistic, but with our calculation of the Chandrasekhar limit, we have degenerate matter. We can repeat the degeneracy calculation for neutrons. The Chandrasekhar, and again, the heavier a neutron star is, the smaller its size, and the details of the calculation are slightly different and not as well understood, because we do not understand degenerate nuclear matter as well as we understand degenerate electrons. But the Chandrasekhar mass, the maximal mass of a neutron star, is not 1.4 solar masses, but 2.2 to 2.9 solar masses. This depends a little bit on details of the model and more on the rate at which this thing rotates. As we will talk, we expect these stellar remnants to be rotating very fast, and with fast rotation, you can support degenerate neutron star with a mass of up to almost 3 solar masses. What happens if the collapsing core ends up being more massive than this is something that we'll leave for next week. So some physics predictions follow from this, and I want to pay attention to them. So I said we expect the remnant of a star to be rotating very fast. This is reasonably clear. If there was any rotation at all in the core, then, this is back to the fun experiment with me standing on the platform. When I pulled the weights in, my rotation sped up. In this case, remember, something is contracting from the size of Earth to 10 kilometers. The rate of rotation would have to speed up. If you think of angular momentum as m times v times r, and angular momentum is essentially conserved, there's some angular momentum loss, but not orders of magnitude, and you remember that v is 2 pi r over p, then ignoring the constants, as we are doing all week, you find that angular momentum depends on the relevant quantities as m times r squared divided by p, and so we can solve for p, right, as mr squared. And if you remember that the mass of the neutron star is about the mass of the core that collapsed, but the radii are much smaller, the period of rotation of the neutron star is related to the period of the rotation of the core by this ratio. So how fast was the stellar core rotating before it collapsed? Well, we can get a handle on this perhaps by looking at the rotation rates of typical white dwarfs, which are, after all, the cores of smaller stars, making some reasonable assumptions. you find an estimate that the period with which a neutron star can rotate might be as short as 5 milliseconds. This is fast rotations indeed. This is something that rotates 200 times a second. An object with the mass of the sun rotating 200 times a second. Similar considerations predict a very intense magnetic field. And the reason is that, of course, by the time you get to a stellar core, everything is ionized. And you remember that we discussed the fact that charged particles interact with a magnetic field in this interesting hydrodynamic way. The magnetic field affects the motion of the charged particles, but the charged particles drag the magnetic field with them. So if you have the magnetic field of the core of a star, as the core implodes, it drags the magnetic field with it. What you have is the same magnetic field confined to a smaller area. The intensity of the magnetic field, if you think about it as some number of magnetic lines, the intensity of the magnetic field can be measured by the flux of magnetic lines per unit area. Since the area is shrinking by a factor of r squared, you expect a huge magnetic field. Again, plugging in what we know about the magnetic fields of white dwarfs, you expect magnetic fields on the order of a trillion times the magnetic field of the sun. There will be strong magnetic effects associated to this. You can make some estimate for the temperature. Remember, I said that at collapse, the temperature was billions of Kelvin. By the time we see the core exposed and the envelope is gone, temperatures are expected to be down to 1,000,000 Kelvin. This means that Wien's law tells us that these neutron stars will at least initially be radiating X-rays at 3 nanometer wavelengths, and given the temperature and the radius of 10 kilometers, you can compute that the luminosity is about a quarter of the solar luminosity, not visible from Earth, but visible to X-ray telescopes. Okay, so these are all nice stories that theorists told. It was a theorist called Franz Zwicky who first predicted that the outcome of a supernova explosion would be this nuclear density collection of neutrons. This was a very theoretical prediction. It was not clear at all that such things could or should exist. The discovery was made by Jocelyn Bell in 1967, and Jocelyn Bell was a radio astronomer. She was looking at interactions of the magnetic field with quasar radiation, but what she found was a periodic radio signal with a period that was very precisely 1.337 seconds, and so there was a blip in her radio signal at the wavelength she was looking at, the frequency she was listening at, every 1.337 seconds, and of course the immediate interpretation was, well, maybe some radio station from some other country is broadcasting a time signal at some weird period. This was quickly excluded. The next idea was maybe these were literally termed LGM signals. LGM stood for Little Green Men. This could be the long-awaited SETI signal of some intelligent being somewhere else contacting us. Maybe it was their version of the BBC. It turns out quickly they turned their telescopes another direction. They found other sources at exactly the same frequency. It was unlikely that civilizations many, many light years apart would all be addressing us on the same frequency, so this is a natural source. Soon many of what came to be called pulsars, these pulsing radio sources, were found. Their periods ranged between a tenth of a second and 2 seconds, so this is a little longer than the maximum rotation period that we expected for neutron stars, but it's within the ballpark, and nothing else rotates that fast. And they were almost universally slowing down. So their rates of rotation were very, very precise. The repetition of a pulsar is such that it competes almost with atomic clocks, but they very slowly and in a regular fashion are slowing down. If you estimate how long it'll be before a pulsar stops pulsing, the rate of rotation is such that a lifetime of a pulsar would be predicted to be about 10 million years. This is an amusing view of the original LGM signal. It was recorded, as was done in the 60s and, I can tell you, in the late 70s, by an ink recorder moving on a rolling piece of paper, and you see here the signals from the pulsar and a lot of radio interference from which it had to be distinguished. This is a cleaned up version of the same over here on the right, and those blips are actually the regularly spaced but not very regularly shaped. This is in fact true. Pulses from the pulsar And so this is the discovery of the first pulsars. So what are these things? Well, I'm going to claim that they're neutron stars. People tried to invent all kinds of other possible models for what a pulsar might be, but you could imagine trying to invent a binary system that rotates every 0.2 seconds. But a binary system orbiting every 0.2 seconds would have two white dwarfs right on top of each other and inside each other, and would very rapidly slow down. You can try to imagine maybe a star that is rotating and has some hot spot that emits radio waves. And again, an order of magnitude calculation tells you something. So how fast can a star rotate without centrifugal forces ripping it apart? Well, we can do the calculation because we know everything we need to. In order for a star to rotate, its objects on its surface must be accelerating towards the middle with the centripetal acceleration that we computed long ago, v squared over r. That's 2 pi r divided by p squared divided by r, because v is 2 pi r divided by the period, and r in this case is just the radius of the star. That's the radius at which of the circle at the equator along which things move. So plugging that into here, I get 1r cancels, and I get 4 pi squared r over p squared. And why would these objects be accelerating towards the center of the star? Well, of course, because gravity is accelerating them. In the case of Earth, we too are accelerating towards the center of Earth, at least at the equator, with this acceleration, but that is a far smaller number than the force that Earth applies to us, the gravitational acceleration g, and so that is why even at the equator we don't float. What I'm asking is how fast does a star need to spin before its equator floats, and then if it spins any faster, its equator will be blown apart. So that is obtained by setting the centripetal acceleration equal to the gravitational acceleration of the star. You can solve this for the period, and here's the result you get, and sticking in a period of around a second, you quickly realize that a white dwarf, the most massive object known to exist at the time, would blow itself apart if it tried to spin that fast. Remember, we calculated it for the Earth, about 2 hours is the period with which it could spin before it blew itself apart. Remember, low Earth satellites orbit every hour and a half. That's about the period. Notice that this is determined completely by the ratio r cubed divided by m, or m over r cubed, which is the density. So we need something much denser, parametrically denser than white dwarf, and only neutron stars turn out to be an object that can exist that is dense enough to survive rotating this fast. And then the mechanism is that the emission is somehow aligned to the star's magnetic axis, and that perhaps, remember, neutron stars are endowed, we expect, with very powerful magnetic fields, and like the Earth's magnetic field, the neutron star's magnetic field need not be aligned to its rotation axis. So if it is emitting light along the magnetic axis, and the magnetic axis and its axis of rotation in this picture over here on the right is vertical, then over a rotation, the magnetic axis sweeps out a cone in space, and if Earth happens to lie somewhere along this cone, then when the axis is pointed at us, we see a blip of radiation, in this case, radio radiation, the detection soon thereafter of the Crab pulsar, with both a period much shorter than a second, and its known relation with the supernova remnant, nailed both the pulsars, both neutron stars as the source of pulsars, and neutron stars as supernova remnants. And so how does this work? Well, modeling a pulsar is a difficult exercise. It's not completely understood what goes on, and the physics that goes into it is a little bit beyond what we have. But the rough idea is that you have this star which is rotating very rapidly. It's got a very intense magnetic field. That means that at any point there's a rapidly changing and very intense magnetic field. The magnetic field, which changes, remember our friend Faraday, a changing magnetic field creates an intense electric field. This is intense enough to lift charged particles. A neutron star is mostly neutrons, but it does have, certainly in its upper layers, protons and heavy nuclei and certainly electrons. They are lifted. In fact, the electric field is so intense that it can almost create pairs of electrons and positrons out of the vacuum, and so it can pair create its own electrically charged particles. These are then accelerated by the changing magnetic field to very relativistic velocities, and they wind around the magnetic field lines, as such particles are supposed to do. They wind around the magnetic field lines and are dragged around. So there's this magnetosphere of charged particles that are dragged around by the rotation of the pulsar. They wind around the magnetic field lines. This accelerated motion around the magnetic field lines emits a characteristic curvature radiation, which is related to synchrotron radiation. This emits preferentially, because of the relativistic speeds, along the direction of the magnetic axis, and so we produce the sort of lighthouse effect. The source of the energy for all of this emission is the rotation, and this is why the pulsars are observed to slow their rotation speeds. In fact, this at the end will answer the question I posed earlier. Why is the Crab Nebula still glowing 1,000 years after the supernova light pulse has passed through? In fact, the energy source for all of the glow of M1 is the magnetic field generated by the pulsar in the middle. In fact, one can compute or estimate the kinetic energy included in that rotation. One knows the rate at which the Crab pulsar is slowing. One can figure out how much energy that means it's losing and compare that to the luminosity of the Crab Nebula. It's a fun calculation, and the results, to within our uncertainties, completely agree. So the entire luminosity of the Crab Nebula is powered by the slowing down of the rotating neutron star that is in the middle of it. Since Bell's discovery, I said that these particles should emit synchrotron or curvature radiation at all wavelengths, and indeed pulsars have been observed in all bands: radio waves, infrared, ultraviolet, X-rays, visible light. The Crab pulsar can be seen in visible light, though it's a tricky exercise to find it. But pulsars do emit at all bands. Neutron stars are extremely exciting systems. You can imagine that just like white dwarfs, when you put neutron stars in a binary system, you can have exciting mass transfer. The physics that describes all of these phenomena is relativistic, and the details are going to be a little bit beyond what we can do. If we have time next week, we might return armed with some understanding of relativity, and we'll certainly meet neutron stars and pulsars in the sequel, but I could not mention them as the most exciting, almost second most exciting end product of stellar evolution. Of course, the most exciting end product of stellar evolution is what happens if neutron degeneracy is overcome in the collapse of a core, and that will be the topic for next week.